This session will be recorded through the presentations, but we'll stop the recording and I'll announce when we stop the recording prior to the discussion portion of the webinar. We will use the recording to help create a report. And with that underway, I would like to introduce Paula Civic with both from the MRBB and ECCC.
Thank you, Matt. Good afternoon, and thank you everyone for attending today's webinar. My name is Paula Civic. I'm the Executive Director with the Mackenzie River Basin Board. As Matt mentioned, this is the second of 2 knowledge sharing seminars. They were organized as a trial because we had heard through our work with the MRBB that there was interest in providing a forum to start to link some of the great work that's going on in this massive basin. And it was undertaken with some of the resources provided in Budget 2022 to sustain the Freshwater Action Plan. In August of 2021, the Mackenzie River Basin Board published an online State of the Aquatic Ecosystem report that shared science and Indigenous knowledge for 4 aquatic indicators in the Mackenzie River Basin. And I'll show you that website in just a second. The topics for the 2 webinars in this series were informed in part by information gaps or knowledge gaps, and also just based on the patterns of change that we observed in the Mackenzie River Basin as a whole and reported in that report. So I'm just going to quickly share my screen and show you the State of the Aquatic Ecosystem report. Can everyone see that, Matt? Great, thank you. So Carter or somebody will share the link to this, what we call the SOAR, State of the Aquatic Ecosystem Report, in the chat. This is the site. I would love for folks to visit it. Send me any ideas or feedback as we are in the process of already starting to plan for the next State of the Aquatic Ecosystem Report and how we can update and change and revise this site. When you visit the site, you will come originally to a homepage. The About section has a lot about the process of the work, the years of work and the number of people that went into developing this report. And then as you look at the 6 subbasins of the report, you see publicly available knowledge out, that we graded for science and Indigenous knowledge for the 4 indicators in the basin. Finally, when you go to the site, there is an overview section which presents some of the basin-wide trends and overall knowledge gaps that we identified while doing this work. The process of actually just compiling all the information that went into the site that you see online took about 2 years and involved at least 25 people. We anticipate it's going to take at least that effort to continue to update and revise the site as we go forward. I'll stop sharing now. Stop sharing. There we go. So today, 4 environment and climate change scientists will share their work on hydrological modeling research and tools. They are Dr. Vincent Fortin, Daniel Princz, Dr. Rajesh Shrestha, and Dr. Yonas Dibike. The knowledge sharing series, as I mentioned, is an experiment. This is only our 2nd time trying this format, but we do hope to provide additional webinars if there's interest in the community and if we have the resources to do so. So given that, we'd also be grateful for your feedback. Close to the end of the session, Carter will share a retro board. This is a place for comments. If you have thoughts and ideas for future webinar topics, but also on the format that we're trying out today. If you see your idea already on that retro board and just want to add your support to it, you can upvote it by pressing the thumbs up button. Feel free to reach out to Matt or Carter or Catherine or myself or anybody connected to this project at any point. Also, if you have feedback to share either on the SOAR or on these webinars. And with that, I'll wait till he finishes drinking his water and I'll turn it back to Matt.
Awesome.
Thank you.
Thanks, Paula. Okay, so the vision for today is a bunch of presentations. We'll have a bit of a plenary session. We'll go into breakout rooms, and then we'll have another plenary session to wrap up the day. We're here to present information to you. So if you have any questions, please feel free to jump in during the discussion periods and ask those questions. We're hoping to have an interactive webinar. And to support that, I'd like to review the process and some ground rules to support this discussion. We'll be posting a recording of the discussions. We won't be posting this recording of the discussion anywhere. We'll just be posting the presentation after the fact. And we'll also be working on a report of this webinar that will go through the MRBB and be on the MRBB website at some point in the not so distant future. The ground rules to keep in mind as we're engaging in some conversation is to keep an open mind, to listen generously, to be respectful of others, and to ask questions to gain an understanding and or clarity, and to speak directly, to say what you mean in a respectful manner. And I think with those in mind, with those ideas in mind, that we'll be able to have a very good, respectful, robust conversation. Have I missed anything? No? I think we're good to go. So our first presenters are Vincent and Daniel. Daniel Princz is a physical scientist with the National Hydrologic Service at Environment and Climate Change Canada. He leads the recent NAS prediction initiative for the West and North regions. Vincent is a senior scientist in hydrologic forecasting research at Environment and Climate Change Canada. He has over 15 years of experience in hydrologic forecast research aimed at implementing operational forecasting systems for various components of the water cycle using Earth system modeling approach. Their talk is implementation of ECCC's National Surface and River Prediction System on the Mackenzie Watershed. And take it away.
Good. Can you hear me well?
Indeed.
Yes, good. So I'll be presenting with Dan Princz, but there are many other people who contributed to the work you'll be seeing today. I don't have time to name them all. I'd like still to acknowledge them. And here's the outline of the talk. So I'll start with just a short primer on hydrological modeling using physically based models. That will hopefully be useful for the other presentations we'll be seeing today. Then Dan will take over and present the hydrological prediction component of the National Hydrological Services Transformation Initiative, which is a 5-year project that's ending a month and a half from now. And then I will come back to present one modeling system that we've developed as part of this initiative, which is the National Surface and River Prediction System. And I'll focus on its implementation on the Mackenzie River Basin.
So Vincent, do you have slides?
See my slide?
Yeah. Can you see my slides? I don't think I was sharing before. We're good? We're good?
Yeah, we can see it now.
Okay, good. Okay, so here's the hydrological modeling primer. I will talk about the typical structure of physically based hydrological models, just one slide on that. There's more details in supplementary materials in this presentation. Then I'll talk briefly about data processing, because these models process a lot of data, input data, and generate a lot of output data. And I'll touch on various operation modes of these models. So they can be used in simulation, reanalysis, projection, scenario, forecasting. There's also model calibration, which I will not touch on in this presentation, but that's discussed in the supplementary material. So let's start with the typical internal structure of physically based hydrological models. So not all models work this way, but many actually do. or there are small variations from this scheme. So there's typically a land surface component in hydrological models that represents vertical processes occurring at the surface that impact the energy budget and the water budget. And then from this land surface component, you get various fluxes that are predicted, such as evaporation, but also runoff. And the runoff output from the land surface component typically goes into a river routing component that is used to predict flows, eventually water levels on the system. So the land information is typically available on some type of regular grid or subbasins and for multiple vertical levels in the soil. Whereas the river, lake, and lake information is available at each node of a model river network, river and lake network. That will typically include each location at which you have measurements. So here's just an overview of the type of data that goes into these models. So typically you will have a digital elevation model that gives you a model orography and helps you estimate slopes and drainage directions. You will also constrain this digital elevation model using a digital river and lake and reservoir network. You will need information on land cover, land use, also information on soil texture. And here, typically, it's whatever you can get because there's not a lot to work with. So this is typically static information, or it will be updated on a long time scale. So land cover can change with time, but typically not every day. Soil texture is typically static. Then you have time varying information that's used to estimate the current state of the system, such as meteorological data, observed water level and river flow. And all of this data is used to estimate the future state of the system or the system at ungauged locations using physics. So you have governing equations that define your model, and then you need to come up with a numerical model, so a computer model that will solve these equations using the data you have. In terms of output, you don't only get stream flow or lake levels, you also get other variables such as snow cover, snow water equivalent, snow depth, soil moisture, soil temperature information, and other diagnostics such as surface temperature, near surface humidity. And these outputs can be obtained based on historical meteorological data, and that's what we'll call a simulation. After introducing a change in the system, such as a new dam, that would be a scenario, based on current meteorological data, that would be an analysis or a nowcast, based on future meteorological data, that would be a forecast, or based on future climate scenarios, that would be a climate projection. Right? That's how basically this model works. If we go a little bit in more details, it tries to mimic how the real world works. So you have inputs that in the real world that impact the outputs that you might or might not measure. To run your model, you need to measure some inputs, and then you will model them. And the model has typically a large number of parameters that need to be set during using calibration procedure to predict some outputs. And the model also has internal state variables such as snow and soil moisture that would evolve with time. And the model will start from some initial state. And an open loop simulation can be used to provide information at ungauged locations. You can also use the same model with modified inputs, and that will be useful for climate change prediction or probable maximum flood studies. Then you can also use the same model for forecasting. This time, you will have measured inputs that will help you figure out what the initial state is through a data assimilation process. And you will have also forecasts of future inputs. So this would be your weather forecast that go into your model and give you some prediction of outputs. So hopefully you've learned a bit how these models work, and I'll with that, turn it to Dan.
Sure, can you hear me fine? So I'm just going to speak to what Vincent briefly mentioned was an investment in Environment Climate Change Canada for what they call a transformation to build new prediction tools. It's just one piece of a larger initiative, but really was focused on bridging and building better connections between the research, development, operations, support, and end user chain to deliver products and services that meet hydrologic prediction of the end users. And in particular, this case was focused on provincial and territorial partners, as well as our own needs internally, but ultimately would benefit all of Canadians. Next. So the reason for this was to support ourselves internally, as I mentioned, to strengthen our hydrometric operations and data services, particularly where information was scarce or hard to obtain or difficult to measure, or we don't have stations. It's also to use for where we do have federal mandate to do studies, do modeling on transboundary watersheds in coordination with the states, for example, as well as to support the provinces, territories, and other partners, and more than anything, do a better job at incorporating their direct needs into our own development cycles and into the development of the products that we produce and provision to them, as well as to the rest of Canadians. Next. So speaking of operations internally, we use these systems to fill data where it doesn't exist. We hope to use it for field planning, things like Vincent mentioned, the forecast, so that we can make better use of budgets, do better planning to make sure that we're sending people when it makes sense for continuous data production, as well as for verification of data infilling based on the ensembles that some of these systems produce. We've done pilots to integrate the feeds of the forecast into our own water survey data systems. These systems are relatively new, so we're still working on it. We've also looked at and will be looking at post-processing and additional statistical work to add value to basically the numbers that these systems are producing and making sure that they make sense in reality. Next. So the biggest benefit of these are where stations don't exist. Water Survey of Canada works with real data. They measure flow where they can. Even where we have stations, we can't always measure it. For example, when rivers have iced over. But hydrologic modeling has the benefit of giving us an answer where maybe we don't have one, or a best guess or an estimate that we can use to connect and fill the dots where some of those gaps exist. It also gives us an opportunity to provide kind of an image or a look at what conditions are now across the country. And on the right-hand upper corner there, you have the current domain of these systems, which cover most, about 50% of Canada, not most, but most places where, with the exception of the West, the West Coast, where a lot of our population exists. And it gives us a benefit of looking at what the conditions are now, not just flow, but things like snow, things like moisture, that can give us an indication of what the conditions are. For example, if a heavy rain system moves in, if some weather moves in, that would have flooding potential. Next. These are some of the examples that we've used where we have transboundary responsibilities. This is international, which is between Canada and the States, but also domestic, which is between provinces. And there's support here for operational forecasting, for improving some of the hydrometeorological data. So again, this is not just flow, but it could be surface conditions, it could be weather conditions, in aiding decision support, climate monitoring, time series analyses, as well as in communications. They've also been looking at using these data for analyses such as floodplain mapping to figure out where river levels or water levels would be, to figure out flooding potential, basically. Next. We've only recently, or maybe it's been a little while now, have these products running operationally, and with that, we've also been able to provision them to the provinces and territories. Now, nearly all of our partners who from the river forecasting centers of the provinces and territories have access through protected layers of GeoMet, which is a data provisioning service that we have. Some of our partners in like Ontario, they've been looking at how they could integrate these data feeds into their WSGI environment, which is a data management software. The Western provinces and territories initiated how they would be able to do the same, but with their Delft Fuse environments, which benefit some of the Eastern provinces as well. We've used these products to support certain analyses. So there's been the Great Slave Lake high water event for the past few years. Great Slave Lake has been seeing very high water levels, and they were using these systems as a group to analyze those and kind of predict how long that would last, as well as for snow analyses. And then we work with a lot of the provinces and territories to see how else we can help them with that if we can. And now we're just also starting to expand that. We work a lot with academia, but also hydropower has an investment in flow forecasting. And so we're just starting to work with them as well. Next. I guess the outcome of this initiative really is to change a bit of the dynamic of which we develop and promote these products, to really try to be better at making them user focused. We have a big push to make them discoverable, accessible, practical, reliable, adaptable. This basically means that hopefully the NHS is providing a bit of a middle point to assist partners in finding what's available, in knowing what's available, with helping them get to it, providing some practical documentation. And then across the board, we're all working and doing analyses to evaluate these products to ensure they're reliable. And moving forward, we hope that they remain adaptable, so that as the systems change and evolve, and as more user needs are identified, we can continue to incorporate them into the development cycle and basically make that chain from development to operations to users more robust. And I don't know if that's it, or is there more? Outreach and engagement. A lot of this relates to connecting with people. So we did host national flood forecasting workshops in 2019, 2021, focused in 2019 on the provinces and territories, because they have the mandate to issue flood warnings across the nation. And then in 2021, a bit more open and with researchers involved to instead display more of what was ongoing in the research community, what's being developed and what's coming. We've also established a community of practice on operational hydrological prediction in Canada, which is chaired by representatives from provinces and territories, where we meet quarterly to discuss their pressing needs. And it gives them a bit of a mechanism to share information with other provinces and territories and kind of learn from each other a bit more easily. We're members of the National Administrators Table. We maintain meetings with the provinces and territories regularly, as well as with other partners like academia. We've developed questionnaires and surveys to gauge how Environment Canada's data is being used or how it can be improved, as well as providing direct support to users, which can be pilot projects or focused initiatives where they have specific concerns of a particular data product or data that's been sent through GeoMet or DataMart. We've also internally established reestablished what's called the Hydrological Prediction Forum, which it's a group where we're trying to do better at incorporating user feedback and making sure that everybody's talking together at the same times, from the producers to the consumers. And is there more? The next slide. And then we have services initiated. So this relates again to the engagement. We are working on practical documentation, tutorials, open source tools. Environment Canada, Canada as a whole, the government of Canada has many portals for finding information, open data. It can be difficult to navigate, or it has all the information available. So we've been working on consolidating that into a hydrological focus. And then as well, we are supporting product dissemination. We're testing the data as well to ensure that it conforms to what the users would expect. And then we do work with community model development through our mesh platform to transfer some of the physics of the prediction systems we have internally to research groups externally, where they're able to validate those physics or improve them, which ultimately could improve our own numerical weather prediction systems. And I don't know if there's more, Vincent. That's it.
Sorry, I was muted. How long do I have left, Matt?
Take as long as you need.
Okay. So I'll give you a bit more detail on the National Surface and River Prediction System and how it's implemented on the basin. I'll give you an overview of the system, illustrate the model's behavior, and show you what verification scores look like, talk about future work. Shouldn't take too long. So here's, in a nutshell, how the system works. So there's an analysis portion that figures out the current condition. And from that, so this is the initial state. From that, we forecast out to a few days up to a few weeks. The observations that go in include for precipitation, in situ observations, radar where available, satellite information. And from that, we map precipitation across Canada and across North America, in fact. And this provides one of the major inputs to the land surface analysis component that figures out what's the snow in the ground, the soil moisture on the ground, and what runoff's coming out of that ground at the initial time. And this feeds into the river flow and lake and reservoir level analysis, which figures out, again, initial conditions in the rivers and the lakes. Then we go to the forecast part, starting with the weather forecast and our land surface analysis. We get land surface forecast of all the same components. And this feeds into our river flow forecasting system that it will give you estimates of flows and lake levels. A bit more details on the characteristics of the system. So for the land surface component, we are using SVS for the land surface model. It's a system land surface model developed in-house at 2.5 kilometer resolution across the country. It has 7 vertical layers, and it provides 6-day forecasts, deterministic forecasts at higher resolution than a 16-day outlook. Once a week, it's actually 32 days. And this land surface component actually covers all of Canada, except the Arctic Islands. The river routing component is implemented on about half of the country, covering most of the population with the exception of BC. It has a 1 kilometer resolution, so it models the main river in each 1 by 1 grid box. And it has the same forecast, 6 days out, deterministic, and ensemble forecasts are available for some watersheds, not yet for the Mackenzie, but they're coming this year. And it includes reservoir models. We try to figure out how we humans are managing these reservoirs in the system in the forecast model. For that, we use the DZTR model, and it's implemented on Bennett Dam these days. Various data sets are assimilated to get initial conditions, in addition to what's already assimilated for weather forecasting. And there's a lot of satellite data going in. So satellite snow cover data, satellite surface temperature, satellite soil moisture, satellite precipitation. For stream flow, it's in situ measurements. Just a bit more details on the DZTR model. So it assumes that you have different rules for outflows as a function of water levels, depending on where you are in the reservoirs in terms of level. And so that you build a curve based on observations of inflows and outflows that represents how these reservoirs manage. It's very simplistic representation of how reservoirs are managed, of course, but it does help us forecast outcomes. That has shown this is shown what basins are currently modeled in terms of the river routing component. This slide shows the gauges that are assimilated to get the initial conditions. So we do bring in ECCC gauges, but also provincial gauges into the system. So all of these points, when observations are available, provide in initial conditions on flows and sometimes water level. We represent explicitly some of the lakes in the system and one reservoir. So these are two different colors you see here. So 40 lakes are explicitly represented. This shows you just maps of what the forecast looked like. So this is a 6-day forecast issued in September of 2020, valid on the 23rd. So the 6-day forecast issued in 17th shows you maps of forecast precipitation, a forecast of soil moisture here, a forecast of surface temperature, and a forecast of runoff. For runoff and precipitation, it's an accumulation over a 6-day period. Soil moisture and temperature, it's an instantaneous value at that exact time. So you can see a few interesting features. So here you have an area where there were forest fires in BC and the northwest of the US. So you can see that there was not a lot of precipitation in that area, but and the soil moisture was the soil was really dry, and the temperature is fairly high. Another area of interest here is Hurricane Sally that had just hit here in the US. So a lot of precipitation, of course. Soil moisture is also here is quite high, close to the coast. Temperature on the cold side compared to the surrounding area, but a lot of runoff. Hurricane Teddy had just hit the Maritime, so a lot of precipitation again, wet soil, not so much of an impact on temperature, and quite a bit of runoff. And there was also an interesting event in the Mackenzie River Basin with some precipitation, not that much, but temperatures leading to snow melt over the course of 6 days. That caused some runoff. We can then look at the stream flow field, but because it's such a high resolution, it's really hard to figure out anything because of the 1 kilometer grid resolution. So we can zoom in more. This is a great slave. I just pulled the forecast for Hay River. Here are daily forecasts, one day forecast stitched together for a period of about 2 months in 2020. So this is the kind of output you can get from the system. I have one slide on forecast scores, but what I want to emphasize here is that before making any change to the system, we always look at some basic scores that tell us how the system is behaving. For example, RMSE normalized by area of the watershed, so the units are in millimeters per day as a function of lead time. Here you see 2 curves, one in blue, one in red. Blue would be the old system prior to an upgrade we implemented in November 2021. So we will only implement an upgrade if we see a significant improvement in some scores and not too much degradation in others. So we want to stay neutral for most scores and improve at least some before we implement any change to the system. That we don't implement things just for the sake of implementing, but because it improves the quality of the forecast are delivered to clients. So this is something and we also look at individual stream flow gauges that are of particular interest to clients. In terms of future works, so innovations that are expected to be implemented this year include ensemble forecasts for the Mackenzie River Basin. So instead of having forecasts 6 days out, we'll start to have forecasts issued 15 days out on a daily basis, then every week, 32 days out. We're also improving the data assimilation method based on the hydrograph separation technique to adjust the base flow contribution of the model. That will reduce biases in low flow periods. And our research and development priorities include improving representation of some whole region processes that are lacking in the model currently, improving model calibration, and including statistical post-processing of model outputs. That's it.
Excellent. thank you so much, Vincent and Daniel. Really appreciate the talk, and I also really appreciate the refresher on hydrologic modeling at the beginning of the talk. So without further ado, I'd like to introduce Dr. Shrestha, who's a research scientist at Environment and Climate Change Canada and an adjunct professor at the Department of Geography, the University of Victoria. His research focuses on assessing the cascading impacts of climate change on hydrologic systems. His talk today is entitled Future Snow Drought and Hydrologic Change in the Mackenzie Basin. And Raj, I'm hoping that you're good to go.
Yeah, I will share my screen. Sure. Can you see my screen?
Good to go.
Okay, yeah, thanks Matt for introduction, and thanks for giving this opportunity to introduce my research to the community here. Before I begin, I would like to acknowledge the contributors who have contributed to this work, who are Barry Bonsall and Alex Cannon from Environment and Climate Change Canada, Marcus Norbus from Pacific Climate Impacts Consortium, Hunter Alford, James Boniman, and Tammy Guo. They are students from University of Victoria, and our collaborators, Mohammad Reza Nazafi and Reza Razvani, who are from University of Western Ontario. So according to the Canada's Changing Climate Report, what we are hearing or what we are finding is that Canada's climate is changing at a rapid rate, almost twice the global average. And in northern areas, Canada's climate is actually warming at much higher rate. That's what we've been saying nationally, but zooming into like Mackenzie Basin here, we see also quite a large warming in different areas of Mackenzie Basin. So we have the recent data from Vincent's group actually. So RDRS2 data that derived from those maps are derived from those data sets, temperature and precipitation. Thanks Vincent for that. So, and then what we are seeing over the winter period, October to March, from 1981 to 2018, is that those basins in the north, in Mackenzie, are warming at a very rapid rate compared to the southern basins. And the warming trends are also quite statistically significant, as shown by the hash lines here. Temperature changes are also mostly in terms of increases. So different areas are showing different levels of increases. They are quite heterogeneous across the basin, but we see some regions in like Liard and Peace basins, which are warming at a much higher rate. Sorry, which are have precipitation increase at much higher rate than other parts of the basin. Looking at the annual maximum sea change, this is from a different data set from Mudrick et al. What we are seeing is that the northern part of basin may be have less amount of snow compared to the historical period, and then the southern areas we are seeing kind of decline. We are increasing snowpack. So those data sets are not exactly the same. So there may be some kind of inconsistency issues, but what we are seeing is that maybe because of the increases in the temperature in northern part of the basin, high increased temperature, we are seeing some decline in the northern Mackenzie, and because of higher precipitation increase in the southern parts of Mackenzie Basin, we are seeing some increase in snow. That's how it is looking historically. So what we wanted to look at was how will that affect in future climate. So we have a couple of research questions that we are focused on in this research. How future changes in temperature and precipitation will affect snowpack in Western Canada. So this study that we did was for Western Canada, not only Mackenzie Basin, but I'll try to focus in this presentation our results from Mackenzie. And then the second objective we had in this presentation was to look at, will there be occurrence of exceptionally low snow or snow drought in these basins? We are interested in the snow for a number of reasons. First and foremost being that snow is a natural freshwater reservoir in northern basins, and it stores water during winter months and slowly releases during during spring and summer months. So that's a great reservoir to have for cold regions. The impact of snow drought or snow loss can be quite varied and considerable. For example, earlier snow melt that comes with the smaller snowpack and also warmer spring temperatures can cause lower runoff and prolonged dry period during spring and summer months. Because of the increase in the winter runoff, there may be a seasonal shift in water supply. So this was illustrated by this graphic from Manu et al. Paper that was published in 2020. So these show that in current climate, we have a higher snowpack and then good balance between winter and summer runoff. But in warmer climate, there'll be a shift towards higher runoff in cold seasons. So this is actually for Western US region. So the changes may be not as drastic as this in Mackenzie, but we'll still see some shift in seasonal water supply. Vincent and Daniel talk quite a bit about forecasting, and snow is an important initial condition for forecasting extreme events or even water supply. So lack of snow or loss of snow can affect our ability to predict water supply and floods, because in many of these basins, the forecast scale that's derived or that comes from snow can be even higher than the forecast that we get from temperature precipitation forecast. So to address these resource questions and assess these impacts, we need models, starting with GCMs or global climate models, which are the models of the world and simulate different climatic change conditions based on different emission scenarios or climate forcing scenarios. So these are great tool to have, but at the basin scale, like Mackenzie Basin or any other basin, the resolution of the output from GCMs are quite coarse to assess the local level impacts. So, and now that number of different approaches that we can deal with this resolution issue. One approach is to use dynamically downscaling or RCM. RCMs are the regional models, regional climate models set up usually at a continental scale, and they are of much higher resolution than the GCMs. So they provide much better variables like hydrologic variables compared to the GCMs. And the RCMs also have land surface schemes which can simulate different land surface processes, including snowpack and hydrologic processes. A second approach is to use statistically downscaling approach. Statistical downscaling is a method that relates climate variables from GCMs, large-scale GCMs, to local scale climate. And based on that relationship, derives high resolution climate data for local scale. And this statistical downscale climate data has to be run through a hydrologic model that Vincent described so nicely for hydrologic projections. So first part of the work, this is based on the RCMs. So we are here looking at temperature projections for October to March for 1 degrees to 4 degrees warming over the Western Canada region. Actually, Western North America, there's some parts like Columbia Basin, which goes into US as well. So for different levels of warming from 1 degree to 4 degrees here, we see that the warming get much more intensified. Like for example, for 2 degrees warming, over in Mackenzie Basin here, we are seeing about 3 to 4 degrees increases in temperature. And for 4 degrees of warming over at Mackenzie Basin, we see 6 to 8 degrees of temperature increase. And the S line here shows the mean divided by standard deviation as the signal to noise ratio. So what we are seeing here is that for all these changes, the noise, the signal coming from the change signal coming from the GCMs or RCMs are much higher than the noises that we can expect when we are considering different GCMs or RCMs. Going on to precipitation projections for October to March for 1 degrees to 4 degrees of warming, we are seeing also increased precipitation for all the levels of warming. For example, for 2 degrees of warming in Mackenzie Basin, we see about 20% increase in precipitation. And for 4 degrees of warming, we see about 40% increase in precipitation. So it's quite an intense increase in precipitation in those winter months, October to March. So looking at the SNOMAX projections, what we are seeing is kind of interesting that in the lower half of this maps here, we see decreases in snowpack, and in the upper half, we see kind of increases, and the differences get more amplified as the level of warming increases. So from 1 degrees, we see a little increase in the north and the decline in south, but at 4 degrees, we see quite intense decrease in the south and increase in the north. So that's the signal that we are seeing. And in the Mackenzie, it's also quite interesting. We see like part of the Mackenzie, we see increases. For example, at 2 degrees of warming, we see some decreases in the lower basins like Princz and Athabasca, but in the upper basins, we see increases in the snow. So how will that changes in the snowpack will translate to changes in the snow drought? That's what we wanted to look at. So the first thing we look at was the changes in snow drought frequencies. So the 3 bars here, so above normal, near normal, and below normal conditions. So by definition, all 3 are supposed to occur 33% of time in the historical climate and no change future climate. So what we are seeing here is that for northern basins like Peel and Liard, the red bars, which is the snow drought bar, we see still these are snow drought is not that much prevalent in those basins. But for the southern basins of Peace and Athabasca, in Mackenzie, we see snow drought start to get more prominent, starting with 2 degrees, and then getting more and more prominent at 3 degrees and 4 degrees of warming in Peace Basin. And the same thing also in Athabasca Basin. And this is outside of scope of the Mackenzie Basin, but for basins like Fraser and Columbia, we see quite intense snow drought even at 1 degrees, and then it becomes more and more intensified with the higher levels of warming. Next, we considered what are the dominant climatic factors or conditions that lead to snow drought. So we looked at the climatic conditions like that may occur in future climate, like warm and wet, warm and dry. So the pink color here is warm and wet. That dominates the snow drought occurrence in all those basins, Peace and Athabasca, and the southern basins, Fraser and Columbia. So that means that even though there's increase in precipitation, increase in winter precipitation, we can expect snow drought to occur. And that also means that precipitation increase is not able to compensate the decline in the precipitation, the decline in temperature-driven snow in this basin. Next, we consider what are the hydroclimatic factors that cause snow drought. Why the differences in the north, not much snow drought in north, and more snow drought in south. So what we did was we looked at the mean basin temperature for those 6 months, October to March, so in x-axis here, against the change in snow in y-axis for all basins. What we found was kind of quite interesting. So the basins in the north, like Peel and Liard, there's not much snow down in these basins because these basins will remain cold even with much more intense warming in these basins. But basins in the south, starting with Peace and Athabasca, we see snow drought becoming more and more prominent at 3 degrees of warming and above. And in the southern basins like Fraser and Columbia, they are starting to occur even at 1.5 degrees warming and even more with the higher levels of warming. What we also found interesting was mean basin temperature of about 5 to 6 degrees is kind of threshold, where above which the snow drought becomes more intense and occur more or less all the time above those temperatures. Next, going on to the Liard Basin study. Liard is an important basin within Mackenzie. It covers about 16% of Mackenzie drainage.
Sure.
Yeah, Mackenzie basin, but it contributes to more than 25% of the discharge. What we are interested to look at in Mackenzie Basin was, in Liard Basin was to see how the amplified temperature and precipitation will affect hydrologic regime in the Liard Basin. So as you can see here, over in the Liard Basin, so the mean annual temperature is projected to increase from about -3 degrees in 1950s to about plus 5 degrees end of century, according to the RCP 8.5 scenario. And mean annual precipitation is projected to increase from about 550 millimeters in beginning of 1950s to 650 millimeters end of century. So how these intense temperature and precipitation change will affect different hydrologic, different components of the hydrologic regime. That's what we're interested to look at. So first we looked at the historical change. So these are the stream flow data from Liard River at the mouth gauging station. We looked at the trends, historical trends in annual mean flow, annual maximum flow, annual maximum flow timing, and annual minimum flow. We see that annual mean flow appear to be increasing, maximum flow appear to be decreasing, maximum flow timing is getting earlier, and minimum flow is increasing. So, although none of these trends are significant, these are the kind of typical trends we expect with the warming climate. So the trends that we are seeing in the Liard Basin is very consistent with what we would expect in the historical climate. So what we were also interested to look at was, will the future change be similar to the historical trend, or will that be some kind of divergence between historical change and future change? So for this study, we used variable introduction capacity hydrological model that is driven by 7 GCMs for 2 emission scenarios, RCP 4.5 and 8.5. We use a modern statistical downscaling approach called MBCN, developed by our colleague Alex Cannon. This method, in contrast to other downscaling methods, maintains realistic relationship between temperature and precipitation. So by virtue of maintaining a good relationship between temperature and precipitation, we can expect improved hydrologic simulation. And big model consists of different algorithms that simulates water and energy balance. It also consists of frozen ground. So it's good for the cold climate environment like Liard Basin, and it simulates different processes like snow evaporation, soil moisture runoff, and stream flow. We also use the results of the big model and the statistical dynamic, statistical downscale climate data to look at which variable is driving which part of the hydrologic regime or which variable is actually dependent on which stream flow variable is actually dependent on which climate variables. First, looking at the temperature and precipitation changes in the Liard Basin for the 4 seasons: January, February, March, April, May, June, July, August, September, and October, November, December. Upper panels are for precipitation change, and the lower panels are for temperature change from 1 degrees to 3 degrees above the global mean temperature increase over the pre-industrial period. So the red arrows are for RCP 8.5 scenarios, and blue ones are for RCP 4.5 scenario. So what we see is that, not surprisingly, for all the GMT increases, we see temperature increase for all seasons. Precipitation is also projected to increase for all seasons except July, August, September, where we see slight decrease in precipitation. We also see much steeper increase for winter months of October, November, December, and January, February, March in both temperature and precipitation compared to the other seasons. So looking at the stream flow projections that we obtained from the big model, we see that mean flow has slight change or a small increase from 1 degrees to 3 degrees of warming. We also see that the range of values we obtain from different GCMs tend to get wider with each degrees of warming. Maximum flow also tend to increase slightly compared to 1 degrees. 3 degrees is a little bit higher, but we also see is like there's large uncertainty when we go to higher levels of warming. Maximum flow timing is getting earlier with is half degree of warming, as you can see here, from about 262 days to about 250 days at 3 degrees of warming. And minimum flow is becoming will become higher with each half a degree of warming, as you can see, from about 430 millimeters to 480 millimeters. So these trends in general are quite consistent with what we are seeing in historic climate. So especially the maximum flow timing and minimum flow, the direction of change and also are very consistent with what we are already observing in the Liard Basin. Next, we looked at what are the main drivers of these changes, main factors that drive these changes. So this figure here shows variable importance, and the blue bars represent precipitation, and the red bars represent temperature. So the longer the bars, higher the influence. So we can see that for mean flow, precipitation plays much dominant role than temperature. And same for maximum flow as well, where we see dominant influence of precipitation compared to temperature. In the case of maximum flow timing, we see the most dominant factor being the April, May, June temperature, which is kind of understandable. That's when snow melt occurs. And in the case of minimum flow, the dominant or most dominant factor is the January, February, March temperature. We also looked at how these variables are related in terms of this gradient plot, where we had temperature change in x-axis and precipitation change in y-axis. And we are seeing some kind of a stratification along precipitation axis. So we see lower values of mean flow at lower precipitation and higher values of mean flow at higher precipitation. So this shows that the relationship is quite strong for mean flow. It is not that strong, for example, for Qmax timing. We see there's not much stratification, or it's kind of quite mixed. So the relationship is not as strong in this case. And in the case of minimum flow, we are seeing also quite a good stratification. So that means that the influence of temperature is quite strong in minimum flow. And for in the case of maximum flow, it's kind of also mixed. So the signal that means that the influence is weaker for maximum flow. And lastly, our colleagues at University of Western Ontario are looking at the future changes in rain and snow events in the Liard Basin, building on the study that I just presented on Liard Basin. So what they have been looking at is the changes in wet days, changes in rainfall intensity, and which will drive the rain and snow events. So what we are seeing right now with the work that we have done so far is that number of wet days will increase for all seasons: January, February, March, April, May, June, July, August, September, and October, November, December, for each degrees of warming, as you can see here. And this is the base period, the blue line, and the dark red is the 4 degrees of warming. So number of wet days will increase for all levels of warming. What we also see is interesting is that rainfall intensity for 3 millimeters of snow in ground. So when there's 3 millimeters of snow in ground, how the rainfall intensity will change. So we don't see much changes for January, February, March, July, August, September, or October, November, December, but we see considerable change towards higher rainfall intensity when there's 3 millimeters of snow in ground. So this tells us that there's a likelihood of higher rain and snow events in the future climate. Obviously, we need to look this into much more detail to tease out finer details of rain and snow events. To summarize, so we see highly heterogeneous pattern of snow drought response across the basins of Northwest North America. Certain basins of Mackenzie, like Princz and Athabasca, are higher risk of snow drought. Future stream flow in Liard Basin indicate small increases in mean flow and maximum flow, and larger increase in minimum flow, and earlier maximum flow timing, which is generally consistent with what we are observing historically. And there's some evidence that rain and snow will intensify in future climate. I'll stop here. Thank you.
Thanks so much, Raj. I think that was really fascinating, and the detailed look that you provided, I think, was really informative. So thank you very much for that. So moving on now to Dr. Yonas Dibike, who is a research scientist at Environment and Climate Change Canada, Watershed Hydrology and Ecology Research Division, and he's located in Victoria, BC. He also holds an adjunct faculty appointment at McMaster University and the University of Victoria. His research interests include hydrologic, hydrodynamic, and transport modeling, as well as hydroclimate analysis and climate change impact studies. His talk is entitled Modeling the Hydrologic Impacts of Projected Climate in the Athabasca Watershed, Implication on Water Availability in the Region. Take it away.
Thank you very much for the introduction. So this work has been done a few years ago, and I have a number of collaborators who worked on this project. I have listed them down here, and it's a joint work between Environment Canada and colleagues from Alberta Environment. So the study objective was, it's part of the Canada and Alberta Joint Oil Sand Monitoring Program, which identifies a need for modeling of the source, transport, flux, and fate of the various chemical constituents in the lower Athabasca. So to achieve this objective, there was a requirement to set up a process-based hydrologic model for the whole Athabasca watershed and perform hydrologic and hydraulic simulation studies corresponding to projected climate scenarios. So the Athabasca watershed is the southernmost sub-watershed of the Mackenzie Basin, and it's the headwater of the Mackenzie Basin, and where there is a lot of industrial activity taking place. And so it's part of this oil sands monitoring program. We conducted these hydrologic studies. So this is part of a bigger modeling framework, which consists of hydroclimate analysis, hydrologic modeling, and also river hydraulics and transport modeling, which also supported by process studies in river ice and sediment dynamics to achieve an integrated river regime modeling, which can be used to project flows, extreme events, sediment contaminant transports, and like that. However, my today's presentation will only focus on the watershed hydrologic modeling aspect of this modeling framework. So the Athabasca watershed is a very diverse watershed in terms of topography, which ranges from over 3,600 meters at the upstream locations to up to 200 meters near the Lake Athabasca, where it drains. And similarly, in terms of land cover, soil type, it's a diverse region. And precipitation ranges from 300 millimeter downstream to up to over 1,000 millimeter at the upstream headwater region. So a very diverse region. It covers around 156,000 kilometers square. And the mean annual flow in the river is at Fort Mac and below is around 600 meter cube per second. So just to see the hydroclimatic variation in this watershed, it's always better to divide this region into three regional difference amongst the three hydrophysiographic regions, where the upper basins, which is glacial and highly snow-fed, and the middle region, which is a boreal forest, and the lower part, which is more flat region. So these three regions have quite different hydroclimatic responses. If you look at the upper basin, the runoff coefficients are around 0.76, which means 76% of the precipitation will end up being a runoff, while in the middle basin, it's only 0.14. That means 14% of the precipitation end up in a runoff, and for the lower basin, it's only 25% of the precipitation end up to be a runoff. And that can be seen in these graphs, where for the upper basin, the runoff is quite high, while the middle basin and the lower basin, the runoffs are relatively smaller compared to the upper basin. So the model we have used is the VICS, the variable infiltration capacity model, which Raj also mentioned, which is a large-scale semi-distributed process-based hydrologic model, and which uses all the topographic, land use, land cover, soil type, soil data. And this is the source of the different data we have used. For the climate data, we have used the NRCan meteorological data, which is at 10 kilometer resolution for precipitation and temperature. And for the other variables like relative humidity, wind speed, we use the North American regional area analysis data sets. And daily river flow data from 7 hydrometric stations is used to calibrate and validate the model. And the model resolution is around 1/16 degree, which is around 7 kilometer spatial resolution. So the first thing in any hydrologic modeling is to calibrate the model. Even if the model is a process-based model, there is still few parameters that needs to be fine-tuned. In this case, we have to calibrate 5 soil and base flow parameters and 2 routing parameters. We have to fit the model using multi-objective function, which is calibrated using the dynamic dimensional search algorithm, DDS algorithm. Not only the flow in the rivers, but also we have to make sure that the snow water equivalent is simulated quite reasonably. And that was good in this case because it has at least captured the variability in the snow water equivalent in the different regions. Say in the upper region, the snow water equivalent range between 300 to 400 millimeter, while in the middle region, it's only between 25 and 100 millimeter of snow water equivalent. And in the lower basin, it's between 50 to 150 millimeter of snow water equivalent. So all this variation along the watershed has been captured by the model. So once we have satisfying model, then the next thing is to do the climate change projection. The climate change projection is based on 6 selected CMIP 5 GCMs and 2 downscaling techniques, BCSD and BCCI from the Pacific Climate Impact Consortium. They did the downscaling to a 10 kilometer resolution, and for the RCP 4.5 and 8.5 scenarios, so a total of 24 hydrologic scenarios. So if you look at the precipitation, this up to 2005 is a historical period. Then this is the climate projection after that. This is for the 4.5 scenario, and this is for the 8.5 scenario. Similarly, for daily maximum temperature, this is a climate projection that's out of the 6 model and 2 downscaling. That means 12 possibilities, and the solid line you see is the ensemble mean of the 12 models. And similarly for T-mean. So as you can see, the T-mean is the increase in T-mean is relatively higher than the increase in T-max in this case. If you look at this in terms of this projected change in temperature versus precipitation, you can see that the projected change in precipitation range from 0 up to 30% increase, and in terms of temperature from 1 to 7 degree increase based on for different scenarios and emission scenarios and future periods. But seasonally, if you look at seasonally, it's reflected the similar things for winters, spring, and autumn. But when you look at the summer, there is also at least half of the models shows a decrease in precipitation as well as increase in precipitation. And also for the temperature, you can see. So the ensemble mean change in precipitation, if you look at it for the full basin, and this is for the upper basin, middle basin, and lower basin, in general, there is an ensemble increase in precipitation and relatively slightly more increase in the upper basin compared to the middle and the lower basin. And if you look at it seasonally, the 3 seasons are increasing except the summer, where we see some decreases, especially in the upper basin. Most of the decrease in summer precipitation is in the upper basin. So this the consequence of this change in precipitation and temperature on the snow water equivalent, you can see here in the upper basin, when the snow water equivalent decrease throughout the year, because there is snow throughout the year at these higher elevations, and there will be a decrease in snow water equivalent, but the highest decrease is in the spring months of April and May, June. That's where the highest decrease in snow water equivalent. For the middle basin, mostly the decrease is in the spring, February, March, April. And for the lower basin, similarly, it's mostly spring, the decrease in snow water equivalent. If you look at the March 1st and April 1st snow water equivalent, which are usually what are used to predict, used by water resource engineers to predict like reservoir inflows and things like that, you see the decrease in snow water equivalent March 1st is, there is a decrease, but it's slightly small, especially except for the RCP 8.5 and end of century scenario. But for the April 1st snow water equivalent, it's almost all cases, there is a significant decrease in snow water equivalent, and especially for end of century and 8.5 climate scenario. In terms of snow cover duration, you can see both for 4.5 and 8.5 scenario, you will see a significant decrease in snow cover duration between the historical and the two future periods. But the decrease is even higher for the RCP 8.5 scenario. As you can see, significant decrease. This is the ensemble mean here. You can see a decrease of between 20 to 50 days in snow cover duration for the future scenario. Then the next thing we see is a change in seasonal precipitation and actual evapotranspiration. Whatever is an excess amount of flow in the basin is a difference between the change in precipitation and the change in actual evapotranspiration. We saw that there will be an increase in precipitation, and we also saw that there is an increase in temperature, which means there will be an increase in actual evapotranspiration. But this map shows us the difference between these two changes. And this is positive, that means there will still be an excess moisture compared to the historical period. And the increase is higher in the upper basin compared to the middle and the lower basin. But if you look at it seasonally, the increases are in the spring, fall, and winter season, but not in summer. So in summer, there will be a deficit. The change between P minus actual evapotranspiration is negative. That means there will be a deficit in summer. And the increase is higher in the winter compared to all the other seasons. So the implication of this change in moisture, and as well as the change in the timing of the flow, is shown in this figure. This shows the change in mean monthly flow. As you can see, the winter and spring flows will be increasing, while the summer flows will be decreasing. That's just the consequence of all those changes in precipitation and temperature we saw earlier. This is for the in a basin in the upper basin, and this one is in the lower basin. This is at Athabasca River below Fort McMurray. So similarly, there is an increase in winter and spring flows and a decrease in summer flow. So a potential increase in spring and winter flows and decrease in summer flow due to the combined effect of increased precipitation and earlier snowmelt. In terms of change in dates of annual maximum flow, again, the date of maximum flow will be becoming earlier. And this is even more obvious for the RCP 8.5 scenario. The blue is the historical period, and the green and red are the future periods. You can see that the peak flow is occurring earlier and earlier. This summarizes all the results in the study. Here is annual flow. As you can see, for a number of stations, the annual flow is increasing. The summer flow is decreasing, and the minimum flow is increasing, as has been shown by Raj also. Minimum flow will be increasing and maximum flow also increasing, but not as much as the increase in minimum flow. And the date of maximum flow is becoming earlier. The other thing we looked at is a change in the magnitude of peak flow. So we did flood frequency analysis based on annual maximum flow. And we found that the frequency of peak flow will be increasing in the future scenario. What you see here is for different return periods, the change in annual maximum flow. And this is based on different statistical techniques, assuming stationary condition or non-stationary analysis and stationary analysis, and using different fitting methods and statistical techniques. But in all cases, you see with increasing in return period, the change in maximum flow is increasing at a higher rate. So it's not only increasing, it will be increasing at higher rate for less frequent events with higher return period. This is the same for all the stations we looked at. This can be looked at in a different way here. What we are plotting here is the historical period, return period, versus the future return period. This is for the end of century scenario. So if you look at here, the 60-year return period flow for the historical condition will become a 20-year return period flow in the future condition. This shows how it becomes more frequent in the future. And this is using stationary frequency analysis. If you use the non-stationary frequency analysis, where the distribution parameters also change with time, this will be even more. So the 60-year flow in the historical period can become a 15-year flow, or the 100-year flow, return period flow in the current historical period will become a 20-year return period flow in the future. So this shows the increase in the frequency of peak flows for the future scenario. So this is just to summarize all what I have said. I don't need to repeat it, this one, so I will just leave it like that. And but instead, these are some of the publications from which I presented today. And we didn't end up just analyzing the hydrology, but these hydrologic projections can be an input to other studies. For instance, here in this case, we have used these hydrologic projections as input for a hydraulic model, so that we can study the impact of climate change on the hydraulics and sediment transport regimes in the lower Athabasca watershed. So here you see that the change in the hydrology is reflected here in the change in the water level, velocity, and change in suspended sediment concentration. The increase in water level in all seasons except the summer season. Similarly, for say suspended sediment transport, it will increase in most months except the summer seasons. This is because the increase in precipitation will generate more sediment from the watershed, and again the increase in velocity and discharge in the river will have more sediment transport capacity. So this way you can use the hydrologic projections as input to do other type of studies like change in water quality and ecology. Here is another work where we used again the output of the hydrologic model to do projection for change in Aboriginal navigation index. That means to study the navigability of the lower Athabasca River. This is just this is a paper which is still under review, but the results shows that especially in the critical months of these are navigable months during from end of summer till the fall, before the ice cover started. This is a critical navigation season. And during this season, the result shows that there will be a decrease in the navigability of the river during this critical time for the future scenarios. This is a historical Aboriginal Navigation Index, and in the future, these are the changes expected for the different scenarios. In the future direction, this Athabasca watershed model has been transferred to the Alberta environment so that they can use it in operational mode, or they can update for different assessments. Currently, they have updated this model with a newer version of the VIC model. They had a higher spatial resolution. They increased it from 1/16 to 1/32, from 6 to 7 kilometer to 3 to 4 kilometer resolution. They have also improved the hybrid climate data set used for model forcing. They have updated the climate forcing for the model, and they have downscaled the CMIP 6 climate scenario. So the next step would be to do the climate projections with CMIP 6 climate scenario and the updated hydrologic model. So with this, I will wrap up my presentation, and thank you for your attention.